Welcome to the deep dive. Today we're getting into something pretty fundamental in machine learning, classification. Basically, how computers learn to put things in different buckets. Cat or dog, spam or not spam.
Exactly. We've got some material covering a few key methods.
Yeah, let's like logistic regression, k-nearest neighbors, and crucially, how we measure if these things are actually, well, working.
Right, performance assessment, it's super important.
So our mission is to kind of unpack these classification techniques, figure out what they're good for, and how to evaluate them properly. Sound good?
Sounds great. It's all about building tools to make good categorizations.
Okay, let's start with logistic regression. Why would you pick this one? What's its deal?
Well, logistic regression is really your go-to when the outcome you're predicting is categorical. Think yes, no, true, false, that kind of thing.
Okay.
And what's neat is it doesn't just say yes or no, it gives you the probability, the chance of it being yes.
How does it do that?
It uses this mathematical function, the sigmoid function. It looks like an S-curve.
Right.
And that function squishes the output, so it always falls between 0 and 1. Perfect for probability.
So that's different from standard linear regression then, because that just draws a straight line.
Totally different. Yeah, linear regression can give you predictions like, I don't know, 1.5 or netties or 0.2. Makes no sense for probability.
Okay.
Logistic regression keeps it bounded, 0 to 1. You see it used a lot in like predicting customer churn. Are they going to leave? Or like you said, spotting spam emails.
Makes sense. Okay, so we build this model. How do we know if it's any good? Our sources mentioned the confusion matrix.
Confusion matrix. Yeah, think of it as the model's performance report card.
Report card.
It breaks everything down. How many times did we predict yes, and it was yes? That's a true positive.
Right.
How many times did we predict yes, and it was actually no? False positive, and so on, for true negatives and false negatives.
Got it. And from this matrix, we get other metrics like accuracy.
Exactly. Accuracy is the most basic one. Just the total number of correct predictions divided by all predictions. Simple.
But maybe too simple sometimes.
That's the catch. Accuracy can be misleading, especially if your data is imbalanced.
How so?
Okay, imagine you're testing for a rare disease, maybe only 2% of people have it. A model that always predicts no disease would be 98% accurate.
Wow, yeah. But it misses every single actual case.
Precisely. In that scenario, you care a lot more about not missing cases. That's where recall comes in.
Okay, so break down precision and recall for us.
Sure. Precision asks, of all the times the model predicted yes, positive, how many were actually yes? High precision means fewer false alarms.
Okay.
Recall, or sensitivity, asks, of all the actual yes cases out there, how many did the model correctly identify? High recall means fewer missed cases.
So in the disease example, high recall is critical. We don't want false negatives.
Absolutely. But there's often a trade-off. Pushing for higher recall might mean you accidentally flag more healthy people, lower precision.
Ah, the classic trade-off. How do we manage that?
Well, that's where looking at both, often using something like a precision recall curve, becomes really useful.
A curve. How does that work?
It basically plots precision versus recall for different decision thresholds in your model.
Thresholds. You mean like how confident the model needs to be before it says yes?
Exactly. Maybe instead of saying yes if the probability is over 0.5, you say yes if it's over 0.3 to catch more cases. That changes your precision and recall.
I see.
The curve shows you that relationship. You can look at it and decide, okay, for this problem, I need at least X recall, so I'll pick the threshold that gives me that, even if precision drops a bit, or vice versa.
So you can pick your balance point.
You can pick your balance point, yeah.
Yeah.
Especially vital with those imbalanced data sets we mentioned.
Is there like a single number that tries to combine both?
There is. That's the F1 score.
F1 score.
Yep. It's the harmonic mean of precision and recall. It kind of gives you a balanced measure. A score of 1 is perfect precision and recall. 0 is the worst. It considers both false positives and false negatives.
Okay, cool. That seems useful. Right, let's switch gears slightly. The k-nearest neighbors algorithm, or KNN. How does that one classify things? It sounds different.
It is, yeah. KNN is conceptually quite simple, actually. It's non-parametric, meaning it doesn't really learn a specific function like logistic regression does.
So what does it do?
It classifies a new data point based on, well, its neighbors. Specifically, its k-nearest neighbors in the training data.
K-nearest neighbors. So you look at the closest existing data points.
Exactly. You choose a number, k, then for a new point you want to classify, you calculate how far away it is from all the points in your training set.
Using something like standard distance?
Yeah, usually Euclidean distance.
Yeah.
Then you find the k points with the smallest distances, the closest ones.
Okay.
And then you just look at the classes of those K neighbors. Whichever class is most common among them, well, that's the class you assign to your new point. It's like voting.
It's like asking the local neighborhood. Interesting. So how do you pick the right K? Is it always 3 or 5 or...
Ah, good question. That's often found through experimentation. You try different values for K, say K1, K3, K5, K7, whatever seems reasonable.
and see which one works best?
Right. You typically evaluate the model's performance, maybe using accuracy or F1 score, on a separate test data set for each K. The K that gives you the best performance, usually the lowest error, is the one you go with.
So you tune it based on results.
You tune it. It's part of the process.
Okay, so we've covered logistic regression using that S-curve for probabilities and KNN using neighbor similarity. And we've hit the key ways to measure success. The confusion matrix, accuracy, precision, recall, and that combined F1 score.
Mm-hmm. And the importance of not just relying on one metric, especially accuracy.
Definitely. Understanding the context, like whether missing a case or having a false alarm is worse, seems crucial for picking the right metric and maybe even the right threshold.
It really is. That trade-off between precision and recall comes up again and again. You have to know what you're optimizing for.
So, wrapping this up, we've seen there are different ways to classify data and different ways to judge success. It really depends on the specific situation.
Absolutely. No single best answer for all problems.
Which leads to a final thought for you, the listener. Thinking about these trade-offs, particularly precision versus recall, can you think of other real-world scenarios where getting that balance right would be absolutely critical? And maybe more complexly, how would you even start deciding which model, like logistic regression or KNN or something else entirely, might be the best starting point for those tricky situations? Something to ponder. Thanks for joining this deep dive.